Hey everybody, welcome to today's video on specific heat capacity. All right, so to start, I'd like you to imagine that you are boiling water for spaghetti and you have 2 spoons sitting in that pot of boiling water on the stove, a wooden spoon and a metal spoon. And if they've both been sitting in that pot for the entire time, I'm wondering which of those 2 spoons would you rather grab? I'm betting if you've done any kind of cooking at all, you're thinking, oh, I'd rather grab the wooden spoon because the metal spoon's going to be really hot. And you're right. So the 2 spoons are the same size and they've both been sitting in the same pot of water, both of them soaking up the same amount of heat. But we would find that the metal spoon's temperature is much higher than the wooden spoons. And that's all because of this property called specific heat capacity. Sometimes we shorten it and just say specific heat. So here's the definition. Specific heat capacity is defined as the amount of heat, that's usually measured in joules or kilojoules, the amount of heat needed to raise the temperature of 1 gram of that substance by 1 degree. Could be a Celsius degree or a Kelvin degree. Both of those have the same size. Specific heat capacity is an intensive property, doesn't matter what size sample you have, and it is unique to each substance. So it's a little bit like density in that way. When you are talking about the density of a substance, it doesn't matter whether you have a small amount of the substance or a large sample, the density is the same either way. Specific heat capacity works in that same way. And because it's unique to each substance, it can be used to help identify a substance. Metals typically have very low specific heat capacities, and then water has, I always call it a freakishly high specific heat capacity. It has just about the highest specific heat capacity of any other substance. The value for water's specific heat capacity is given here, 4.184 joules per gram degree, but I would like you to be in the habit of using that value with the unit written double-decker style, not with the slanty line joules per gram degree, but instead joules over gram degree. You'll find if you write it this way in your calculations, that's way more helpful. All right, so water has this really large specific heat capacity. And one of the important ramifications of that, it has huge implications on our planet, which is covered with a lot of water. So big bodies of water, lakes and oceans, can soak up a lot of heat without changing temperature very much. That is typical of substances with high specific heat capacities. I'll come back and talk about that a little bit more later on. All right, next thing I have for you this equation that relates specific heat capacity, this is the symbol we use for that, relates that to mass and the observed temperature change, and then the heat energy that is absorbed. This equation we will use a lot, and we often refer to it as the mCdeltaT equation. But at any rate, it has this relationship, Q, the heat energy, is equal to mass of the sample times its specific heat capacity times the temperature change that is observed. 2 more notes here about heat energy. If something hot is put into something cold, the heat energy is transferred, and it's always going to move away from the hot thing. It'll be lost by the hot thing and gained by the cold thing. So common misconception, if you hold out your hand and put an ice cube on it, it's going to feel to you like the cold of the ice cube is going into your hand. That's not the case. Instead, the hotter thing, in that case your hand, is going to lose heat energy to the ice cube, and the ice cube will gain that heat. When we do our problems in the lab using calorimetry, we'll use this equation and this idea a lot. All right, so let's now look at a scenario in which we're putting 1410 joules of heat energy and we're applying it to 134.8 grams of water. And we observe that the temperature of the water rises by 2.5 degrees. Okay, let's do a little bit of labeling. So this amount of joules, that is your heat energy Q. And the sample of water has this mass, I'm going to label that M. And then the temperature of the water rises by this much. Notice we're not being told what's the starting temperature and then the ending, but instead just how much it changes. So this is your change in temperature. Delta T stands for change in temperature. All right, then the other part of this scenario is to apply 1410 joules, same amount of heat energy, to the same mass, but this time it's the metal lead. So here's my mass of lead, and we're going to observe that the temperature of the lead rises or changes by 80.3 degrees. So that's the temperature change for the lead. Okay, same amounts of heat, same masses of samples, but in the case of water, the temperature goes up only a little, and in the case of lead, the temperature goes up a lot. So I want us to explain that using a calculation of specific heat capacity. All right, so we are going to use our mCdeltaT equation, Q equals M times C times delta T. But I want us to calculate the specific heat capacity for water. So to do that, I want to isolate the variable C. So I'm simply going to divide both sides of my equation by M times delta T. Okay, so that removes them from this side of the equation. And we end up with C, specific heat capacity, is equal to Q divided by M times delta T. Again, I just performed algebra manipulation on the mCdeltaT equation to solve for C. Now, for water, I'm going to substitute in this value of Q and the value for the mass and the temperature change. And then I grab my calculator, 1410 divided by, okay, parentheses down here, the product of open parentheses, 134.8 times 2.5, close parentheses. And that gives us the specific heat for water, 4.184, which is what we should expect because water's specific heat capacity is unique to it. Every sample of water, whether I'm talking about the whole entire ocean or a pot of spaghetti water or a spoon of water, specific heat should have this unique value. Notice that in my problem, joule in the numerator, gram and degree Celsius in the denominator, those are all different units, none of them cancel out. So here's my unit for specific heat. Now, let's do the same thing for lead. Here's the mCdeltaT equation. We're going to solve for C. So same equation here. And now we're going to substitute in the same Q, the same M, but the temperature change is different. And when we grab our calculator and type in 1410 divided by parentheses, 134.8 times 80.3, close parentheses, then this is our answer. Lead has a very small specific heat capacity, as do all of the metals. Water has a much, much higher specific heat capacity. So what I want you to notice here is that if your specific heat capacity is a small number, then the temperature change observed is going to be large. Lead only has to soak up 0.13 joules of heat for each gram to go up by a degree. And another little absorb 0.130 joules, it shoots up another degree. Absorb 0.13 again, shoots up another degree. So you can see that the temperature change can go up, 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 and the delta T will end up being large. However, if you have a substance whose specific heat capacity is large, then the temperature change should be small. Water has to soak up all of these joules before its temperature can go up by a degree. And then it has to soak up another 4.184 joules for the temperature to go up just one more degree. All right, so to go back and recap, specific heat capacity, know the definition, know that the unit, joule per gram degree, is kind of a bulky unit. Know the mCdeltaT equation that relates specific heat capacity to temperature change and to mass and to the amount of heat absorbed. And then when we do our calorimetry problems, keep in mind that any substance that starts out hot and then is placed in contact with a cold substance is going to transfer heat from the hot thing to the cold thing. Okay, I want to finish up with one more thing, and that is to compare two other quantities. This one, called molar heat capacity, is very similar to specific heat capacity. Instead, it's the heat needed to raise the temperature of a mole of substance by 1 degree. And then the last one is this term called heat capacity, not specific heat capacity, but simply heat capacity. That's defined as the heat needed to raise the temperature of an object by 1 degree. So here I have two samples of water, a big bucket of water and a tiny spoon of water. Even though the specific heat capacity of water is always this value, if you are simply talking about the heat capacity, then you would say this big bucket of water has a much larger heat capacity than the tiny spoon. Think of it this way. Let's suppose these were both boiling. Doesn't this bucket of boiling water have a greater capacity to burn you than the little spoon of boiling water does? Again, that's just simply because it has a larger mass. Okay, guys, so I hope that the idea of specific heat capacity is starting to make intuitive sense to you, and we will do lots of work calculating with it using our mCdeltaT equation. Okay, thanks, guys.